Welcome to the 984th monthly meeting. Today we have a speaker, Dan Caselden. He's going to speak to us about neural networks and our sun's missing neighbors. So before we begin, I wasn't sure if John Reed's family is here or not. They were and they left. Okay, we wanted to hear a couple of words from them, but I guess they left. So anyway, then I'll just start the rest of the. So it's a slight segue. I hope folks who attended the NEAF meeting had fun. A few of us were there. I thought the CubeSats were pretty interesting, but it's kind of non-personal way of doing astronomy. But anyways. I thought in the beginning I'll just have a little segue with the trip I had last month. I went to India. I wasn't here for the presentation, and Kerry did it. So I wanted to show you a segment of the trip where I went there. There was the spring equinox, and there is a particular event that was of interest to me. I actually timed my trip accordingly. So
Can you turn on the lights a little bit?
Find white butter.
okay.
Thank you.
All right.
How much that?
Wow, look at that.
All right. So I was in Trivandrum, that particular area, which is about 8.5 degrees above the equator, and that's from where our February speaker Anand also hails from. So I was there, and on the day of the there's a particular temple there. It's about 1,500 years old, and it's a large architecture. And on the day of the equinox, the sun sets, and you can see the sun setting through the particular windows they have created. So here is the temple further down. I'm sorry, can you see that? No. Here is the temple further down there, and this is a close-up view of it. It takes a little bit of time to come up. Yeah. This is a very beautifully architected temple. It's about 1,500 years old, and it is completely carved. And they used a technique to find the exact east-west. They didn't have the magnetism as a means of, so they used the east-west finding this location. I guess many people are familiar with this. A very simple way of finding using the shadow of the sun. And so the architecture looks like this. And so on the day of the eclipse, what happens is that there are 5 windows there, and each window through which the sun goes through every 5 minutes. And it's a pretty cool sight to see that it is quite accurate. And there were a lot of news media and people were there. I was there on March 21st, so it is March 20th was the day. So I missed it by a day, but still you are able to see about the previous day and the next day. You should be able to see it. It's within that 1 degree plus or minus. And so here it is. So it's a pretty crowded area. There are about 5,000 people there watching it. And as it came down, it started getting cloudy. And it looked more like this. You can see somewhere there the sun is there and then disappeared. So we didn't see the thing, but there were a lot of people and the news media there. And in reality, it would have looked like this as it goes through. It is a picture that was taken in 2017 on September, the autumnal equinox, and that is that's what I went for. But anyway, going forward, so if you go approach the temple, you will see these machine gun people. The question is why, right? So that's where the spice story comes up. In Kerala, where the city, that area is from, the kingdom there sold spices and tea for a couple of thousand years at least to their knowledge, and they used to get gold, silver, and diamonds in exchange. And they had collected, and when I left India 45 years ago, I did not know about this. It was only found out about 15 years ago that this temple had a lot of cellars underneath it, and it was all filled with this gold, silver, and everything. And it is considered to be the richest temple in the world, and the total value being about $1 trillion. Now it is connected, I think the last evaluation last year was like $1.2 trillion. And it is surrounded by these cops with machine guns. So that's why you see that.
So who owns the money now?
It is actually owned by the royal family there, and you're not supposed to open and use it. So the general consensus was you cannot go and dip into it. It's sitting there. Anyways, I thought that was interesting. I wanted to share that. I also went to this, I think I once mentioned in the newsletter about this 1834 observatory that was created, second observatory in India, where the Maharaja of that time created this. And it is still operational, and I also, there is a what is it called?
Transit instrument, that's
Transit, yeah, so that is there. So when they see the star pass by, they adjust the sidereal clock, and at 5 o'clock in the morning, the brigades fire a gun, and that's how they announce the time. And
Is that you?
that was me, yeah. And this is our speaker I met finally, and there is a 14-inch scope inside there, and I thought it was fun. They do public outreach, and I also joined one of their public outreach events. So yeah, that's what I wanted to share quickly with my last trip. So I think from there, I will go to Rich and, right?
And we ducked out. I don't know why this came to me, but that was the actual caption too.
No,
Who stole
really?
my plans? That's what I want to know.
Actual size.
So this is a quote by Brian May, lead guitarist for probably the best rock band ever, Queen, also an astrophysicist. Astronomy is much more fun when you're not an astronomer. And I hope that when Glenn and I come up here every month and we blab on about stuff, we hope you get the idea that we're hoping that you find this to be very much fun and not a lot of work. That's what amateur astronomy should be, at least for everybody in this room. And when you get out there under the stars, we sincerely hope that you truly have fun doing it. And I told folks for years, I yell at myself sometimes, on any given night, if it starts to feel like it's work, I just put it all away and come back some other time, because it shouldn't be work at all, it should be a lot of fun. So.
And I've always maintained, when you go outside and you see this cloud and you go, then it's time for a break. That's when I get out the fishing rod and go after bass and trout.
I keep trying to take Glenn fishing up to Stop and Shop, but he doesn't want to come up. All right, next slide, please. Where are we at? This is a March recap. So we had a total lunar eclipse. You know, I was not here last month. Glenn and I sort of proved that the world is not flat by our mutual observations from here and out in California. I was lucky enough to have some clear skies out in San Diego, rare in the evening. Out in San Diego, the marine layer oftentimes rolls in and that's it. But I got some nice shots of the partial phase, and I saw some nice shots of totality. Don't enlarge those too much, they're just handheld memory shots. It rained on me about 15 minutes before I took this shot. That's how the weather out there is crazy. That stuff comes off the ocean and it's just crazy. But quite a few folks here in New England, a lot of our members, got to see the eclipse as well. And so the next bunch of slides are just, you know, the images people send to Glenn and myself. So we'll just go through them pretty fast. I don't know if we want to spend a lot of time on them, because they're right there of the eclipse. Everybody, how many people saw it? Did anybody not see it? I mean, I know it was kind of cloudy here. It was a little bit cloudy, but there's a nice shot from Al. Joseph, nice shot.
Takes a second to move.
Next slide, please. There's a Mark Helton shot. Justin Lutz, very nice. It was killing me that I didn't have a telescope out there in California. I almost bought one. Just for the eclipse, but my wife said no. Joe DeShane and Mike Brown. I love the, Naz had this great shot with a nice starry background. It looks really pretty.
Pretty stars.
Very nice. All right, next slide, please.
Yeah.
And this from Dennis DeChico.
That's nice.
This is a montage of eclipses over the last many years, 2003, 4, 2008, 15, 19, 22, and 25. And
And again, I'm gonna jump in on this one.
sure,
This one right here, October 28, 2004, that's a very important date. Anybody know what happened on that day?
I do.
Won the World Series.
Yeah,
Red Sox, yep.
And I wrote in my column in Astronomy Magazine, I said, that's the real reason. It was nothing to do with any of the players, Ramirez or the Big Papi. There was an eclipse of the moon, and that just turned all the stuff upside down. I remember going from the game out back out to watch the eclipse. They did have a, you know how if you ever watch a baseball game, night game, they love to show the full moon. And it just happened, they were showing glimpses of the moon when it was being eclipsed. So memorable eclipse, right? The greatest eclipse ever, right
I
there.
said to my kids that night, I'm going to be out in the driveway. If it looks like the Red Sox are about to win the World Series, please come and get me. And they did, and I saw it, and I was like, cool, that's nice. I'm going back out to look at the moon. And that's what I did.
I know, is Dennis, by the way, is Dennis with us?
I don't know.
He, I'll tell you, when I initially saw that slide, because I requested, could you send me your favorite, and I saw this, who took all these pictures, but I realized it's a montage of all the different eclipses in the past. You can compare the differences. And sometimes they're very dark. I remember one eclipse I looked for from the clubhouse, and the moon was so dark in totality. I had a 13-inch reflecting telescope, and I could barely see the moon with that much aperture.
Was
So
that
sometimes,
was 92.
somewhere I know it was back in the
It was
past.
about a year and a half after Mount Pinatubo when the Philippines
Yeah.
erupted. And the eclipse was so dark that I had a group of people out around my 20-inch telescope. And even in the 20-inch, you could barely see the moon in the sky. It was that dark because of all the aerosols and dust that the volcano had kicked up into the stratosphere.
But all this is the equipment that Dennis used. Was just, I think it was a 6-inch aperture if I recall, but he used the same equipment for all those different pictures you saw, just for comparison.
And this is a shot from my son's backyard, palm trees, clouds, moon. And Zach Seinberg was at Boston Common in the middle of the wee hours of the morning. Crazy. Anyway, time marched on and we reached Venus's inferior conjunction. So that's a picture I snapped on the 23rd of March at inferior conjunction. Daytime image, very boily, very, the air is very unsteady. But there was the nice razor thin crescent. Next opportunity to see that is on October 24th, 2026. And Venus will be 6.5 degrees away from the sun. So again, another one that's, it's not even sport really. 13 solar diameters away from the sun. You can actually sweep for a little bit in that area and not worry too much about falling onto the sun. So, well, we'll talk more about that when it comes around. Next slide, please. And then on the 29th of March, we had a partial solar eclipse. I saw none of it. I know it was pretty cloudy across New England, but
We do have a video
There's a
clip.
do you
video.
want to put a video on? Okay. This is a video from Russell Cox. That's a still image from Russell Cox down in Rhode Island. Yeah, I yell at folks when they're singing like that. I'm trying to watch an eclipse. Stop singing. But that was a nice shot through the clouds. I like that. And I think there's one other image from Dwight Lampher up in Caribou, Maine. Had some nice clear skies, and that's a view on the Hestia module with the little device that you put your iPhone onto it, and you can take some pretty cool pictures. Anyway, that was a little quick roundup for March. Moving into this next month, the lunar X will be visible on May 4th around 8:15 in the evening. I don't know if you've ever seen it. The lunar X is a play of shadow and light, visible for a couple of hours, right around first quarter. And so this is a nice opportunity, evening, for you to check it out. It's just a little X. It's just the raised rims of a few craters that look like an X for a couple of hours, and it's kind of fun to look at. Jupiter's still around. It's high in the west at sunset. setting around midnight. Again, try twilight observations. Superior conjunction is on June 24th. Mars is still disappointing, 114 million miles away with a very small disk, magnitude 0.6, still near Pollux and Castor.
Nice lineup, in fact, right now.
Yeah, there's a nice lineup of those stars and the planet. Uranus is setting around 10:15, mag 5.8. At the Carlisle Star Party, some kid came up to me and asked me if I could put the telescope on the planet Uranus, and I said, of course I can. And so I then started telling folks, I left it on there for a while, saying, it's going to be the least impressive thing you'll see all night. But ask your friends who amongst them have ever seen the planet Uranus. And so they got a chance to look at Uranus at the Star Party, pretty cool. Next slide, please. There's a group of planets in the morning sky, Mercury, Venus, Saturn, Neptune. With the exception of Venus, the three others are fairly difficult to observe. Remember, we're still in the early spring. And in the northern hemisphere, before sunrise in the springtime, the ecliptic runs very low to the horizon. So even as the elongation of these planets increases, as they are, the Earth, we move in a better position, and they move further away from the sun, they're still really low in the sky at sunrise, making them pretty challenging to look at. Again though, try naked eye observations or telescopic observations of Venus. It's currently 27 degrees from the sun, 11% illuminated, greatest brilliancy at minus magnitude minus 4.5 occurs on 27th of April. And the greatest elongation occurs on May 31st. The moon will join the morning planets on the mornings of April 24th and 25th. Nice photo op, nice really thin crescent moon. There's a new comet in the sky. Perhaps you've heard of it. A couple of days ago, it was given the official designation of C2025F2. It's Swan 25F. And so it's low in the sky just before sunrise. Bob King had an excellent article this morning on the Sky and Telescope's website. So I would encourage you to go look at that and read about the comet and his observations of it. But it's very skirting the morning horizon. Next slide, please, is a more detailed chart. That, again, these are from Bob King's article. And you can see it coursing through the star fields of Andromeda into Triangulum as the month wears on. Perihelion is on May 1st. I read, I think it was in his article, that it will become visible in the evening sky for a while. But after perihelion, I believe it dips for the southern observers to enjoy it. So we won't see much of it after that. But if you're up early, it's about, I think it's about 7th or 8th magnitude right now. Maybe a little bit brighter. But there you go, new comet for us to look at. I did not put a slide up here about there's a nova in Sagittarius, but it's so faint, and it's only about 10 degrees above the horizon, right before sunrise. I figured it was almost an impossible observation, but you can look that up online as well. It's near the teapot of Sagittarius. Let's see what's on the next slide. Let's see what's on the next slide. I guess that's it. There must be no more astronomy to talk about. The double star of the month. It's the triple star of the month. See, Benno, that was on purpose. Benno texted me this morning, he goes, there's a big red thing on one of your slides. But yeah, I put it there. Beta Monocerotis. Beta Mon. If you've never seen this star, it's a fabulous triple star. It's a fabulous triple star. And so the AB components are 4.6 and 5th magnitude, 7 arc seconds. BC is a tighter pair of the 5 magnitude primary and the 5.3 secondary. They're all B3 spectral class stars. So they're really pretty to look at. And it's just, Glenn, you're a double star.
Oh, in fact, at the Carlisle Star Party on the 1st of April, I had that one in the telescope. I was using a little 4.5-inch telescope, and I think the magnifying power wasn't that much. It's probably about 70, 80 power in that area. And the one that's top of these two right here, the BC components, they're only about a little under 3 arc seconds apart. So if the seeing isn't that good or you're using low power, you'll just see this base as a double star. But the three are all about the same brightness. That's what makes it such a spectacular. It is the finest triple star in the entire heavens. Beautiful, and you can see where it's located. I went by the belt of Orion, and it's kind of, if you look at where Sirius and the belt of Orion, you kind of follow and you get to the Beta right there. I remember one time at the clubhouse, in fact, I was trying to get people to look at double stars, and there were some people that were wasting their time on faint fuzzies. And I think it was, who was the president before me?
Neil.
Neil. he had a 7-inch refractor. And he had that on beta monos, and that was just the 3 crisp images. I was going crazy. Get over here. It's hard. I almost had to drag people, but just forget those faint fuzzies. This is something, the 3 points of light. It's beautiful. So if you get a chance, check it out, because it's a spectacular sight.
That's why I picked it. Okay, next slide. I didn't put a variable star of the month up, but Glenn, why don't you talk about these guys?
Okay, the first one was the one, this is last month. That I
Wait,
collected all the
but you know T Corona Borealis still hasn't gone off yet, right?
Well,
We're still going on. You're always still paying attention to that, right? Oh, okay, just checking.
I told you, when I die, it'll happen that night, it'll go into outburst. Okay, 2419 NGC, it's a globular cluster, and it's very faint. It's kind of, I looked at it with my 10-inch telescope, just a little fuzzy patch of light, but what makes it important is it's one of the most distant globular clusters in our galaxy. In fact, in 1930, around 1930, they took a measurement. This thing at that date said it was about 100,000 light years away. And right away, that can't be part of our galaxy. It must be moving in. So they called it the intergalactic wanderer. I think it's actually intergalactic. There was some other phrase, and I forget what it was.
Interloper.
Interloper. But anyway, I could see it with a 10-inch. And we got a couple of pictures of it. This is Doug Paul's original picture right here. We'll show you the other ones. By the time the next slide comes in, it'll have moved another 100,000 light years away. All right, here's Doug's Paul as a close-up. Again, it's a very faint globular because it's so far away, but if it were at the same distance as the M13, it would shine about the size, apparent size of the full moon. So it's a very large globular cluster. Now that's a close-up view right there. We got some other ones. We'll see how they were arranged. Oh, by the way, Doug, did you have any comments on yours? We'll back it up if we can. I don't know how slow those slides are.
That was 3.8 hours, and in the prelim image, which was just up there a moment ago, those 2 bright blue things on the right are halos around 2 bright blue stars.
I'm going to talk about one of those stars in a minute.
Yeah, those are the halos. So the cluster is, of course, on the left.
And that's with what aperture again?
6-inch refractor.
6-inch. Okay, next. All right, Mark Heltons. Is Mark with us?
Yep, I'm here.
Give us the specs.
416 millimeter new ASCAR 65 PHQ, 533 camera, and let's see, 1 hour, because I have a new Skywatcher mount, and I was trying it out for the first time. This is first light. The cool thing about this image, though, is not only can you see the globular, but there is NGC 2424, which is, I think, right in the upper left corner.
Oh, yeah, right in the galaxy.
It's been kind of fun shooting stuff wide field lately because I get to see where everything's sitting in the rest of the universe.
Yeah, I'm not sure what star this is, but I know that for me, I had the star hop to get there, and I had the star hop because this is a very faint constellation. I had the star hop from Castor, which is 7 degrees further down. It was kind of a nice journey, and Castor is a great place to start because that's a spectacular binary pair. Okay, thank you, Mark.
Thank you.
And Anthony Glass, a little closer view. Is Anthony with us?
Yeah, I'm here.
Okay, specs.
Yeah, it's 140 millimeter refractor, a little bit under 4 hours, a lot fainter than I was expecting, but very cool target.
Okay, next slide. Thank you, Anthony. Dave Giordano.
Yes.
Dave?
Yes, sir. Hi. Yep, this was taken with, this was 11 hours over 3 nights, using my Edge 8-inch, Edge HD 8-inch SCT and ASI 294 MC Pro camera with a Beta moon and sky glow filter. And yeah, the subs, I just, taken, these were 10-minute subs, and even looking at those, I was shocked to get the detail after stacking because it was so faint to each of them. So definitely pleased with the end result compared to looking at the subs.
I want to point out something, and I'm the double star fanatic, and this actually is one of the Struve double stars. He around the 1830s. He did an all-sky survey, looked as far south as he could go. 9th magnitude stars in bed, and he cataloged over 3,100 double stars, and this is one of them. It's Struve 1118. And I was visiting this area of the sky years ago with my little 3-inch, that Edmund Scientific Space Conqueror, and I was able to split this one. This is 8th magnitude here. This one is almost 11. There's about 25 arc seconds here, so it's an ample distance, but boy, that was a tough one to see with that little scope, because you're almost talking 11th magnitude. And that scope was advertised as being able to see down to 10.5, so it was kind of a nice split. I like the colors there. I guess that would be kind of a solar type star if those colors are true. All right, next slide. See how many we have left. I want to thank everybody that took these pictures, by the way. We have, there's Mario's. Mario, go ahead. I know you're here.
Yep, I'm here. Well, I'm in Florida. This is taken with the 32-inch f6.5 and with the 6200 camera. I believe it was an hour, maybe 70 minutes of exposure, if I remember correctly. 5 minutes subs and stacked.
Looks like you caught some galaxies in there too.
I always get galaxies.
Look at how impressive that cluster is, though. And again, I think we got a sketch that I took here too, or a sketch I made. We'll go to the next slide. I think that would be the next one. It's probably the first sketch. And this is that whole area again. That's the cluster. And for me, it was about 2 arc minutes across in size. That's about all I could see. And there's a double star right there. Okay. By the way, a few more people this time got involved in the thing. So the next one I'll show you. Let's go to the next one, in fact. Oh, we are already there. Okay, this is NGC 3893 and 3896. It's a galaxy pair in Ursa Major. It's not far from Chi Ursa Majoris, and it's down right about in this area, right up in here, just about a degree away. I did check it out with the 10-inch. I've got a sketch which I'll show next month. The brighter of the two is about 10.5 magnitude. The fainter is more like 13.5. That's a tough one to pick out. I was only able to see the brighter of the two. But that's our challenge for this month. So again, get out there, take some pictures, make sketches.
If you go back one, this is the, just to give you an idea what you're up against. So one back then.
It's coming.
This is it right here. That little guy right there.
Yeah.
So sometimes these objects are pretty faint, but they're still readily visible in, medium to large size telescopes. When we get to the slide about when the clubhouse is open, if you want to see any of these things, we can always turn the large 25-inch scope onto these objects, and you can see them with your eyes. So go ahead, next slide, please. Sorry.
Okay, this is that the same?
No, this is
the one for May.
This is the one for May.
Okay, it's another galaxy pair. It's NGC 4290, 4284. 4290 is the brightest. This one's even tougher. I did try this, just kind of a half-baked effort, and I couldn't see them with a 10-inch scope. The brighter one is about 12th magnitude. The fainter one is more like about 13.5, so they are on the faint side. You'd need some dark skies. What's frustrating to me is I was researching this today, because I haven't started writing the article about it, but Phil Harrington had a piece in Cloudy Nights. He's the one that wrote that book on cosmic challenges. And he was talking about these being a challenge, and then I read what he saw with a 4-inch refractor. And I said, you gotta be kidding me. Yeah, Steve is shaking his head. But again, if you've got the dark enough skies, and I remember again, back in the day when I lived in magnitude 3 skies, or magnitude 6 skies, with my little 3-inch Edmund Scientific Telescope, I saw everything in the Messier catalog, all the galaxies, right down to something around 11th magnitude. So you just need the dark skies, you need a trained eye as well, but we're losing that. And I'd love to find out from Phil, where was he observing from? Because he lives on Long Island, and I don't think there's a place there that's going to have magnitude 6 skies, maybe. But anyway, that's our challenge for next month, just a preview.
There was a star chart slide of that. Is that did I mix them up? Is it the next one? See what the next slide is.
No, we're back at it. That's why I get confused. It should have been a finder chart too. It's located near Delta Ursa Majoris in the Bowl of the Dipper, and it's just that far from Messier 40, another double star, a very unimpressive double star. I think they're both about like 9th to 10th magnitude, about 50 arc seconds apart. But it's right in the same area of those as that particular double star. So that's the one for May. So get out there and start looking.
If you click back to the slide that has the star chart for Ursa Majoris, we can show you.
Yeah.
Let's go back to that one.
That's why I got thrown off, because
There-
it should have been a finding.
I don't know where that slide went, because there was a slide for the finding chart for these guys. No, go back, go back, one more, go right here.
Okay, it's right up there. Whoop, nope, not there.
Go one more,
It's that way, you gotta go this way in that field of
go
view.
one more forward.
There we go. Yeah, right up here. That's where M40 is as well, and those two galaxies are right there. So you have two that are right near Chi. And by the way, just below Chi, there's another galaxy that had a supernova a number of years ago, and I was able to see that one with a little 3D scope. That was kind of a neat thing. But the other one is right up here, just outside the field of Delta. So you got two pairs of galaxy pairs coming up, one this month and one next month.
And the way to find the ones for next month, click ahead one slide down. So this may well be 70 Ursa Majoris. This, I believe, is Winnick 4, that's M40.
Kind of looks like it would be, yeah.
Kind
it's
of,
in
it's
that
in the
area.
right place. And Doug managed to capture this like almost 17th magnitude galaxy in that picture. So nice job.
With a
This one's
6-inch.
relatively easy. This one's really hard. But it's worth having a look. Just go out there and, check it out.
Again, that's 4 hours of total exposure.
Yep. Perfect. All right, onward. So this is out of Keppel and Sander. Their ratings for these objects and the magnitudes and more importantly, the surface brightness of some of these galaxies. When it comes to looking at galaxies, it's all about the surface brightness of them. If you've got something that's a 14.6 magnitude surface brightness, that's going to be a challenge. In Framingham, these faint fuzzies just melt into the sky glow. So it's hopeless in Framingham for me to look at these things. But from the clubhouse with the big telescope, some of these things are pretty easy to find. So anyway, I think that might be the last.
We've got there is that spring introduction to the spring sky.
Dana, what'd you do with some of my slides?
Disappear? 1 second.
Oh, no.
Now, while they're figuring it out, understand, I put together a slide deck and I send it to Rich and it's already garbled.
Oh,
So he has to ungarble it and then he has to send it to Vinu, so we apologize.
really?
I don't have it. Down 31 seconds.
Hmm.
I'll just announce without the
Well,
slide.
the slide that we're talking about was when the clubhouse is actually open, the Friday, Saturday schedule. It's on the event calendar if you look on the website. But Glenn and I were going to do an intro to the spring sky.
25th of April, 8:30 to 10:30, I think was a time element. And then that Saturday after, the 26th, and I don't have the dates, but a week from then, it'd be the next set of rain dates as well. We'll put it out on the internet
Yeah, we'll
anyways,
send out an
'cause
email.
we need to do a sign up for that, but we certainly welcome any of you that are trying to get yourselves familiarized with the spring sky if you're a newbie, or again, you're a veteran that's kind of out of practice and you want to do a little brush up, we invite you to come out with us. So again, the 25th, it's a Friday night from 8:30 to 10:30. We'll look forward to having you
The
there.
makeup dates are Saturday, April 26th, Friday, May 2nd, and Saturday, May 3rd.
Okay. All right.
All right.
I think that's
Well,
probably
And
it
it's
for
in,
me.
by the way, mention it's in the newsletter. It's in the newsletter.
Okay, in the
Perfect, thank
newsletter.
Dan is our speaker today. He's a computer security researcher and citizen scientist living near Boston with his 2 daughters. By day, he builds products that detect unauthorized access to computer systems, but when the kids are asleep, his work shifts to detect faint moving objects in the sky with the American Museum of Natural History. Dan has discovered thousands of nearby brown dwarfs, including a very weird accident that may be the first example of a white dwarf from the galactic halo. For his contributions to brown dwarf science, Dan was awarded the Gordon Mayerson Major Achievement Award by the Astronomical Society of the Pacific and the Chambliss Amateur Achievement Award by the American Astronomical Society. The topic is neural networks and our sun's missing neighbors. Thanks to modern space-based infrared surveys, 2 of the closest known systems to our sun were discovered less than 15 years ago. Both systems contain brown dwarfs, not stars. Brown dwarfs form like stars, but have too little mass to shine by hydrogen fusion. They are cool and glow dimly in the infrared, which is why these neighbors were only found recently. With these such discoveries, it is natural to wonder what else we are missing. This talk introduces varied approaches to discovering new brown dwarfs in infrared imagery, such as citizen science and machine learning. It highlights one weird brown dwarf, its follow-up with the James Webb Space Telescope. Sorry, I don't know what happened there. And the haunting uncertainty of which of the newest and the faintest candidates are real. So, Dan?
Hello, I'm Dan. Thanks for inviting me and feeding me. All I was told, this presentation is contingent upon that, so. Neural networks, yes. So normally this is what I do. I go after or try to frustrate bad guy stuff with computers. So these are, cybercrime folk who are trying to get money or national security threats, but more or less who want to bust up their operations and hopefully pass their info on to the FBI and be very happy when they get picked up, such as this guy who ruined one of my vacations. Science happened. It happened a long time ago. I don't really know how it was that long ago, but it began with an exercise bike, I guess. Riding exercise bikes is very boring, so I bungee corded my laptop to the exercise bike and encountered at one point an article that said, if you're staring at your computer, why not stare at these pictures for us? These pictures are science pictures and you can help science. How? Well, you can find the next Planet 9, that's what it said. Planet 9 is, if you're not aware, a hypothesized planet in our solar system. It's not been found, but the data set that they were combing through, they had a not so secret secondary objective, which was to find brown dwarfs in there. The data set is in the infrared, which is where brown dwarfs shine best. This project is called Backyard Worlds Planet 9. Now, the closest system to us is Alpha Centauri, and it was found in 1689. After that was Barnard Star. It was over 200 years later, quite a while. And then we had two new ones in rapid succession. I'd say recently, in comparison. Why? Well, they're brown dwarfs. And the intro said what brown dwarf is. I don't know how familiar everyone is with the concept of a brown dwarf. The unfortunate part is nobody really agrees on what it means. So some say it's a body of stuff with mass between 12 and 75 Jupiters. Others say as long as it formed like a star, but is not burning hydrogen, then it's a brown dwarf. That means it could pass that brown dwarf to planet mass regime. No one's agreeing right now. Thankfully, we're more or less talking about things that are kind of on the comfortable kind of side of that mass, where we can say they're firmly brown dwarfs because maybe they were ejected from a solar system at some point, but they're probably formed by like a star. So they are hard to find because they're not burning hydrogen. They are faint. They're not emitting much light. They're just glowing in the mid-infrared. So infrared telescopes are how you find them, and infrared telescopes are new. So these folk, Davey Kirkpatrick, who led this project, he's one of the Backyard Worlds Planet 9 people, to try to map out everything within 20 parsecs. So the idea there is if you can say, oh, we know how many stars of this type, stars of that type, brown dwarfs of this type, etc., are within 20 parsecs, you can get an idea of how our galaxy generates stuff. And from that, you can kind of get an idea of maybe some physics about it. But what he found is that the sample is still incomplete. We put a lot of work into trying to make it complete, but once it gets down to 450 to 600 Kelvin, it is not complete up to 20 parsecs anymore. And the colder and colder it gets, the less and less complete it is. And the coolest one, with the currently coolest known object, known brown dwarf, only has that one object in it. And that's weird because it's so close. So where are the others? We found that one, and only that one, that is that cold. So where's the rest? So finding these guys, pretty much everything's been with WISE. That's the Wide Field Infrared Survey Explorer. It is a telescope that was put into space and takes infrared pictures. This is what a few of the bands smushed together look like. I believe this is W1, W2, and W3. And the green blob kind of a little bit on the left of the almost circle would be WISE 0855, the one we just talked about, the coldest one. And the thing beneath it is something in the background. If you were to take all the images that it's taken over the years, and by now it's taken a lot, and stitch them together into a movie, you get something like this. This is the same object. This is only two bands. The bands W3 and W4 were no longer able to be used when cryogen ran out on the spacecraft. They could only keep it cool enough to operate the two shorter bands. So this is, W1 is mapped to blue and green, and W2 is mapped to red and green. So green is the average of the two. That's why it's orange instead of red. And it looks like a snake noodle because it is moving very fast. Each of these, I wouldn't call them exposures, images, is made about every 6 months apart. So this is a star moving this quickly. How we look for these, we're primarily using the images and data taken from the images from WISE. But the first way that people went about it was with catalog searches. So to generate catalogs for this data set, a team will collect all the images, do some really terrible things to get a good idea of where they're actually looking in the sky and smush them together, and then start trying to find points of light in them. That may look like you smooth the whole thing a bunch and subtract it out and then look for any really bright pixels and then try to fit around that pixel. Just weird algorithmic man-made tricks to get an idea of like, where are my little circles of light in this picture? Count them up, and how bright are they, in which of my bands, emit one line on a spreadsheet for each one. That's your catalog. Here's an example of one of them. This is the Legacy Surveys viewer, and this isn't WISE, by the way. You have the different magnitudes that this object was measured in, the number of exposures each one got. So every catalog is more or less unique because the images behind each catalog are completely different, as were the instruments that took them. Sorry, I should say that with these many, many rows, scientists will come up with ideas for what something should look like. Say, I'm looking for a brown dwarf, I might say, it's gonna be brighter in Z and fainter in G and R and maybe I than most other things. So then maybe I could, subtract like R from Z or G from Z and then kind of sort and look for things that are that outlie in that way. And you tend to get tons and tons and tons of, maybe you call them false positives, contamination from other classes of objects that way. So you might do other stuff. For example, like, oh, we know it must move. And if we know it must move, then its position probably doesn't coincide with that of an object that was imaged there 10 years ago. So you can say, all right, exclude anything that's near an object within 3 arc seconds as of this data set 10 years ago. Weird tricks, just pile them up and pile them up and pile them up. And that's what you'll see in some of the papers. It's like, hey, you know, if we said if this number is bigger than that, that number is smaller than that, this minus that is bigger than that, and it didn't appear in this other catalog, then we looked at it with our eyeballs. Another approach, and this is how I came in with Backyard Worlds, was, well, there's lots of enthusiastic people out there in the world, why don't we just let them look if they want to look? So the data's, for WISE anyway, is public, but it's not like you just know it's there. I didn't even know it existed until they publicized it and helped organize people to look through it. So what you're seeing here is one of the actual flip books from Backyard Worlds Planet 9, and that's 0855 again. It's the brightest thing there. This is, compared to what we ended up doing many of our side searches on, a pretty big field of view. And if you're looking for something really, really faint here, it would be pretty tough. So this was a hard project. But despite that, we got a lot of people. You know, the prospect that you could find something actually beneficial to science was compelling for a lot of people. Some of them tried it a little bit, some of them stuck around a lot. Some of them went on to become PhD students. Some of them became, they're observing on IRTF. Like they just go, there's a high school student that just went off to, where did he go? A good school. The community here is incredible. Davey Kirkpatrick, the person I mentioned before, mentors an unbelievable number of students and just trains the whole field up from the bottom. It's very impressive to see. Tom Bickle's one of those people. He is in school now, but he was not physics beforehand or anything. Now he's very deeply in this. This is a quote of him presenting research from the Backyard Worlds community at a brown dwarf conference. And by our calculations, about half of white dwarfs were discovered through the citizen science process. Not necessarily all with that same style flipbook, but all citizen scientists that were corralled by professional scientists and instructed on how to go about things. White dwarfs, I don't think I've mentioned yet, are the coldest of the brown dwarfs. There's L, T, and Y. L is the brighter, hotter, T are in the middle, and Y is the coldest by far. Is there something after Y? I don't know. If you've been staring at a lot of rows in a spreadsheet and sorting them, you've probably at some point been like, there's probably a better way to do this. Enter machine learning. You can feed a model a bunch of examples of known brown dwarfs in catalogs, a bunch of counterexamples of known non-brown dwarfs in catalogs, and train it to do a good job. You may do some feature engineering, like you would pass in that G minus Z and R minus Z instead of just G and Z, or not, and see what it gets. It will take in a row and it will output how brown dwarfy it feels about that row. After you get a highly scoring row, you get to stare at it because there's false positives. You stare at a lot that when you get a good one, you might celebrate. And you might need some eye drops. Once you have a good one, which you can say by looking through this data set, hey, it moves, so it's clearly close. And it's like there every time, doesn't change brightness at all, so I'm pretty sure it's real. Then you could stare at it with a different telescope. We were using Spitzer primarily. Spitzer channel 1 and channel 2, those bands are very similar to WISE, W1 and W2. Channel 3 and channel 4. 3 and channel 4? Yes. So because of that, they're great at both detecting brown dwarfs because they have a band similar to W2, but you can also get photometry that you can map back to WISE photometry, which could be helpful for calibration, as you'll see later. Because it is a stare at my thing telescope and not a survey all the stuff telescope, you can also get deeper measurements, and it was precise enough to get parallaxes. So let's say you've been doing this machine learning thing and you're kind of frustrated because the catalog is becoming a single point of failure. Like, the catalog needs to do a good job of detecting objects. It needs to not confuse when two objects are close together, and it needs to detect objects that are faint. And having a lot of familiarity with telescopes, I'm sure you're all very comfortable with image stacking. So you may not be able to detect an object in one exposure. What if you can detect it in 5? Well, that would be great for for building catalogs, but what when that object moves? You can't naively stack it, or you'll just smear out the signal. There are approaches to this, like a brute force approach, where you say you do a grid search of different trajectories and do detection over a shifted and added stack of images. But we'd rather do detection directly on the images and let the model figure out all that nonsense. So that's what we set off to do. This project is called SMDET, and it inputs the image stack directly. It has been not too fussed with, and then tries to output moving things that are faint within that image stack. Within there, so at the very beginning, these are the inputs. You have the 2 bands, W1, W2. It was set to take 13 images of each band, and it passes it through a series of convolutions. So convolution, this is a 3-dimensional convolution. With a 2-dimensional convolution, you imagine you have like a grid, and you have a operator called a kernel that kind of slides across it and performs some mathematical operation on the things that it touches along the way, and outputs a new grid. With a 3-dimensional convolution, same deal, but it's 3 dimensions, and in this case, the 3rd dimension is time. If anyone has been studying neural networks, you may have heard of a skip layer. That is what you see along the bottom. So you can follow kind of the data flow here, where the images come in at the top, they get kind of screwed with and screwed with and screwed with. They encounter an LSTM, which is another type of layer, and then the data gets passed back into another stack of these guys and sent along the skip layer. So the skip layer, we've found some years ago, helps models that are trained through gradient descent, with their gradients being able to not be fuzzed out by floating point errors before they reach layers too far back in the model. Updating the parameters of the model happens from the end to the front, and if it were all just one linear model, at each step along the way, it accrues floating point error. So this is a technique by which you can somewhat mitigate that. So to train this, we had synthetic objects that we added to real images. Now, we use synthetic objects for a few reasons. One of the big ones was we wanted to be sensitive to objects that we hadn't found yet. We didn't want to only be able to recover objects like ones that we already have. We wanted to find things even fainter and even faster. We had thought of kind of other ways to do that, including screwing with the data, or like trying to use white dwarfs as training data, which you'll see later are bright in W1 but faint in W2. It's the converse of brown dwarfs, funnily enough. But ultimately, having actual 100% knowledge of the ground truth that you're training against is also really helpful. So knowing exactly which pixel has exactly which value lets you train your model really well. So what you see here, this is one output. The object mask is trying to output any faint moving objects that are in the field of view. Then seg, the segmentation mask, it's saying which of these pixels are capturing 1% or more of a faint moving object's flux. If it is, it gets a 1. If it's not, it gets a 0. So these are two objectives that were trained simultaneously with this model. To build these, the final training images, we take these object masks, we take counterexamples, which would be slow-moving bright objects or variable sources, and we take the real data, we add it all together. That's what you see at the bottom. The circles here are positive training examples that the model is told to find. So I'm going to try to play a video of the model as it trained. It will show on a medium bright object what the model outputs were at the beginning and how they improved over time as they trained. So at the top left you have the input, at the bottom you have the two outputs. So you can see as the guy trains, it gets better at both reproducing the object and it's getting the correct color here. So brown dwarfs, as you saw before, are orange in this data set. And the segmentation mask improves as well. At the very end, it's slowed down and co-added further to give you a better idea of the actual physical object we're talking about. Now, this is a white dwarf. And as I said before, white dwarfs are very faint in W2. They're brighter in W1, but comparatively faint in W1 as well when considering shorter wavelengths, like visual. So other surveys like Gaia, for example, have kind of pegged white dwarfs. They can detect them much further out than WISE can. And the astrometry on Gaia is phenomenal. Because of that, it's an excellent source of training, or not training, validation for us. So we took the little cutout of the sky where SMDET was evaluating, and there's a white dwarf there, and this is what it looked like training. It's sped up because it takes a lot longer. You can see it kind of starts picking it up, and that's only on the object output here. And it's bluer this time, which is a good thing because the white dwarfs are bluer. And then the segmentation mask starts picking it up. Each of these training steps is, I believe, 16 training examples. So this thing is just chowing down images. By the end, it starts to get it, comes in, it comes out. It gets more and more consistent. Until ultimately it feels like it's somewhat reliable. And this is near the end of training. If you co-add all the images together, this is what you see. So I don't know about you, but I cannot see in the single images anything in here. Despite that, the model can detect this object just fine. So this is the loss as it trained. The model was fed with a pretty high learning rate, training examples, and anytime it stopped learning, a snapshot was taken, and or rather, anytime it achieved a better loss, a snapshot was taken. And manually, I would say, it doesn't seem like it's doing better anymore, so let's resume an old snapshot and start over. This procedure is called reduce LR on plateau, but I do it by hand because. There's 3 series in here. The dark blue one is the segmentation mask, and the light one is the object mask. The average of the two is what was trained, what the actual loss that was used to train the model. So here's a gallery showing how well the final model did on real stuff. At the top, there's our old friend, WiseWay 55. It's extremely bright, and if the model did not find it, we would have a very big problem. After that is the accident that we'll talk about more. It's faint, but you can still kind of see it in the circle. And then you have an example, white dwarf, I think the one that we were training on before. I can't see it at all. So I consider that good evidence that this is capable of detecting things below the single, I wouldn't call it exposure, but single image detection threshold. And lastly is a real discovery from this model that you can kind of see a little bit of orange here, a little bit of brown. This is a very crowded field. And crowded fields present a significant challenge to the traditional catalog-based approach, because you just can't do many fancy tricks when you have tons and tons of objects on top of each other. Of the sky, there's a density of high-ranking detections. This here is the galactic plane. I would love to say these are all true positives. They are not. I think this might be the Sagittarius A supernova. There's this effect where, I forget the actual physical processes, but some light is like scattered back at us, like it bounces off of material on the far side of the supernova and bounces back at us. It was being called light echoes, and what it ends up looking like is kind of these filaments that just appear and fade out in the image set. But in some cases, those filaments look like really convincingly like moving objects. So I can't blame it, but these were emitted because I am lazy. This is the ecliptic pole and the north and south ecliptic poles. WISE, the way it surveyed, it went around the Earth and hit over the ecliptic pole over and over and over and over and over again. So there's hundreds upon hundreds of co-added images at each pole. And unlike the rest of the sky, they're at weird rotations. So it's more of a computational mess trying to do work there. However, because there is so much data, someone with a much better GPU could probably find some cool stuff there. This here and there is, we're still trying to figure out what's going on here. So this is the equatorial poles, is that a thing? They are, for whatever reason, showing like the co-addition in the backing image set we're using seems to have gone wrong. Something in the image pipeline seems to have gone wrong, and we don't know what that was. So with all of the regions of sky that this model examined, it output all of these things, and these things are just sequences of video. That's not too helpful. You need to do something with that. Like, you can't look at each video, or what was the point of making the model in the first place. So at first I had trained a completely another neural network to analyze the output of that, which it turned out was totally necessary and actually a little harmful. It would have been better off, I later found out, to use the outputs in a more human way. So the segmentation mask tells you which pixels you care about. The object mask shows you the object that's supposed to be there. If you multiply the two together, then the segmentation mask will clean away any scatter, background, and anywhere else the model screwed up. And you're more or less just left with the object that you care about as it moves through video. And that's really easy to do measurements on. We just took the centroid of we took the highest pixel in there and then took the, I think 8 pixels around it. And instead of using a classifier, we just added those up and ranked the results by it, and it was better. It's really frustrating. And then we got these numbers, which are actually great. So you have the brightness here, W1 magnitude on the x-axis as measured by us of the model's output, and W2 here, versus the output of Davy Kirkpatrick's project measuring brown dwarfs, and these brown dwarfs in particular with Spitzer. As mentioned before, Spitzer's photometry is great, especially in comparison to WISE. So this is an excellent ground truth for us. And we can see that it agrees well, but there is this linear offset. And that would make sense if you think back that the segmentation mask only collects pixels that contain 1% of flux or 1% of flux or more, then it is intentionally discarding some pixels that contain flux. So there should be some discrepancy between the two. And we can do a simple linear regression to address that. I would say there is some slight skew going on here, and there's also a bit of question about how the Spitzer 3, whichever one's equating to W1, is behaved over time. This is proper motion that's been measured here on the bottom, and that agrees very well too. These are the results of the survey compared to other surveys of the same data set. Where it excels is where we specifically designed it to excel, which is in faint objects that are moving quickly. Reduced proper motion is used as a proxy for distance in some places, because in general, the closer an object is to you, the higher proper motion it will appear to have. But for us, we wanted a measurement of kind of the difficulty of detecting the object. And reduced proper motion combines how quickly an object is moving with proper motion and how faint it is. So because of that, it's a good metric for how hard is this to detect. It ignores other important stuff, like is it in a crowded field? Are the images taken of it junky, etc. But on its own, it's a pretty good metric. And it did a good job there. With that, I stared at very, very many examples, sorted top to bottom, and at some point, I couldn't do anymore. Enter citizen science again. So we started another citizen science project and fed the outputs of the SMDET project to Backyard World's Cool Neighbors. So instead of it being a wide field that people look at and say, where in this could a moving object be, they're presented with it centered on the position found by our regressions earlier from the model output and saying, is there something that moves here, yes or no? Okay, so we mentioned this in the very beginning, and then we saw it in the middle as an example, the accident. So the accident is it's very weird. Most brown dwarfs that are cool are red. They are brighter in W2 and fainter in W1. And if they're closer, they most likely have higher proper motion. So we're accustomed to seeing things with very high proper motion that are brown dwarfs being very red, because they are, not all of them, but If they're close and we didn't know about it before, that likely means it's a cold brown dwarf. Other surveys would have found it. So that likely means it will be red. This one was close, or rather it was fast, so it was likely close. It was not known, but it was not red. That was a very big, what is this? One may think at first that maybe it was just something missed, which does happen, but it didn't appear in any other imagery either. So we got follow-up. You can see, so the top four here are Ys, and this is the first epoch, W1 and W2, and then the second epoch, you see it moves down and to the right in, oh yes, channel 1 and channel 2. Spitzer, this is it taken in 2019. It's moved further down. And we took it in J-band on Keck, and it is not there at all. As you'll see soon, that is weird, extremely weird. This is with Hubble, HST, and you can just barely see it in Hubble. This is it here. What is it doing? There's nothing out here. So this sequence is saying, show me Spitzer channel 1 minus channel 2 colors on the x-axis, and show me J minus channel 2 colors on the y. So it's taking those two colors and putting it up there and seeing kind of how the population spreads out. And what you tend to get are earlier type brown dwarfs. They pass through the transition from L to T dwarf, and then you get the T dwarfs that pile up here, and eventually the Y dwarfs up here. Nowhere does something come here. However, this might stand out. This is a subdwarf. It's old. It's metal poor. And it's kind of cheating in that direction. So this was our leading hypothesis. Like, it's got to be this, or an ejected planet, or aliens. We don't know. It turns out it was. We later got follow-up with JWST, and the spectrum they are still working on putting together and publishing. It is weird. It is extremely weird. It is extremely metal poor. This has kinematics that are consistent with the halo population, and the metallicity is consistent with the halo population, which would put it at the coldest known object from the halo population. We're pretty confident that's what it is. Open to rebuttals. There's also a new species of silene, I believe they were seeing in there, that they were not seeing in other brown dwarfs at all. And this is being presented hopefully in Nature soon. But that really begs a question. Why was there one? We've been staring at these things forever, using all these methods. Why is there just one that we found? Like, it's faint, but it's not that faint. Our methods can go another full magnitude. SMDET, the model, found it immediately. It was right at the top. Why are there no more? Is it really the case that there's only one near us? So as we continue to push through more examples, we started to find things that we were less and less certain are real. The accident was initially found by accident. That's why it's named that. I had a system before SMDET that was not very good. and it pointed me at this one position in the sky and had a really high score. It's like, this is it, man. This is what you should stare at, and it was nothing. But down at the bottom left was the accident. So I vowed that I would call the next one the on purpose. But I don't know if it's real. And I don't know how to prove if it's real. And if you can't prove if it's real, how do you get telescope time?
Looks like Conway's game of life.
Yeah, we've been staring at these things for some years. Here's another potential one going down. It may be the coldest object we've ever seen. Or it may be nothing at all. Here's another one, left to right. Same thing. So I've been trying to quantify this, and this is my current problem. Give me some percentage likelihood that this is real. Give me some metric I can run over all of the candidates I've found and show me in decreasing likelihood how likely each one is real, and then show me what the likelihood for this one is. And it doesn't work. I don't know how to make it work. I started by doing difference imaging and subtracting the SMDET model from the difference images and seeing how close to zero does that subtraction take it. If the model's right and the difference imaging is perfect, which it is not perfect, but if it were, then performing difference imaging and then subtracting the model would leave you with 0. So it seems like, yay, how close to 0 do we get? But there's problems. If you have a really large field of view, you can see with the poor difference imaging, there's going to be errors everywhere. And the signal, if you were to call it, that of the pixels contributing flux to this object get washed out by the large field of view. If you use too small a field of view, you're cutting off information. Similarly, should the pixels 4 pixels away count as much as the pixels in the middle? We tried PSF weighting, so taking the point spread function of the instrument and multiplying the loss of each pixel by that, and it was an improvement. But there's still problems there. Tried competing models. So what if instead of one moving object, I were to model 2 stationary objects that came in and out of brightness? Does one of those beat the model that we put forth of a moving object? But despite this all, I cannot find a metric that gives me a concrete answer that I can put in front of a telescope allocation committee and say, look at this, it's important. So it would be JWST. But you gotta convince them first. Neo Surveyor will be coming up. It'll probably be a really good candidate. But it's not here yet. It'll be doing searches at a similar wavelength regime, and it will be more sensitive. So, anyone know stats? Guess that's it. You got questions? Yeah.
The introduction said the 2 closest systems were recently discovered because they're brown dwarfs and there are no stars. Are there actually no stars?
Those 2 systems, the hosts, is that what you call it, are brown dwarfs. So there's no star in those systems. That's why the systems are so faint.
Assuming the brown dwarfs formed through accretion, how can that be? There'd be no stars.
The amount of gas that coalesced together was enough to form a compact-ish object, but not enough to sustain hydrogen fusion.
Throughout the whole system?
Yeah. One of the 2 is a binary, a brown dwarf binary. And it's an open question, at what mass, like how low can it go? How low can we spit out balls of these things that stick together, and for how long?
Are you able to determine composition of these objects?
So the spectra that we're getting from JWST are amazing. These objects really shine in that 4.5 micron regime. Before that, we would get spectra from the ground, kind of in J, H, K bands, and we would see a fair amount of information that allows us to make this sequence, this LTY sequence, and get an idea of kind of what molecules we're looking at from a high level, but nothing like JWST. When we got our first one back, it looked like it was like wrong. There were just all these squiggles everywhere. It's like, that can't be real. Like, those can't be real lines, and they were. The sensitivity is insane. With that, they're able to do individual retrievals by running tons and tons and tons of simulations on the, if you were to have this, and this, how much light will be emitted here, here, and here, and here, how does that match to what I see, and just repeat, and they can get much more precise measurements on how much of what is in there. That's why we know the metallicity and the presence of silane in the axon.
What led you to the CNN LSTM architecture?
It was a cool thing at the time.
So, okay, so we're talking like 2015.
Hush you. I think it was like, I don't know, like 2019, something like that. It was when I had my second child, and I would read papers and be very upset that the thing wasn't learning, while she was being very upset of I don't know what.
Yeah. How many GPUs do you need?
If you were going to do a great job, more than I used. I used one to train it, and it was a pretty cheap one. Initially, I was doing it all on AWS, and that wasn't super cheap, despite the GPU being cheap. Later on, when I joined the American Museum of Natural History, they gave me access to their supercomputers, and I got to use nicer, funner ones. So it trained on one, and I want to say it trained for like a month or two. It then ran using an array of them spread across the country at different universities, but it wasn't too many at a time, like 8 to 10 at a time, and it surveyed the whole sky in about a day. Maybe 2 days, something like that.
I'm curious, the path, the direction that the action is moving, is it at a high angle to the galactic plane? The reason for that is, if the halo is really big, and we're only a small fraction of the way out from it, you would expect they would, this far in, they'd be spending a very small fraction of their lives anywhere in our neighborhood. There'd be a statistical likelihood that they'd be going in a fairly high angle galactic plane and be near their paragalactic, whatever, minimum distance to the center of the galaxy. Because this far in, they'd be, much closer than usual. So I'm wondering whether that's part of the reason why there are a lot.
I don't know. We'll have a tentative RV, presumably in a paper very soon, that should give us the full velocities, full space velocities.
But to the first order, do you know whether it's path? You'd expect, most often the path would be the high.
I don't know. I can take a look later.
Yeah, but I wonder whether that is part of why you're not seeing it in them, because it's such a tiny fraction of their lives in our neighborhood this close.
Yeah. Yeah, that would make sense. It still begs the question, like, why we got this one? And, like, did we get lucky? You know? It's the same with 0855, like, why did we just have this one WISE 0855? Did we get lucky? Why is it so close to us? We should be, based on our sensitivities, finding them out much further than we have. Why haven't we found any more? If they're that rare, why is there one right next to us? On CNNs and LSTMs, I tried just CNNs, it's okay. Tried LSTM heavy, okay. UNETs was the thing at the time, tried that. Did better and better and better the more and more and more the UNET I took away until there was no UNET left. And ultimately having the CNNs plus the LSTMs just gave the best results on this data set. I've not tried transformers yet. Yeah. Other questions?
Is it okay if we stop sharing? Somebody was asking.
Oh.
I can turn it.
Yeah. Does that mean no questions?
Charles.
He's clapping.
Do you have a website?
The viewer we're using is on a website, but SNDET itself doesn't have a website. It has a paper that I've been working on for a long time. You will see in some publications prior, like Caselden 2024, in prep. It's now Caselden 2025 in prep.
Okay, well, thank you.
Okay, thanks everyone.
Thanks everyone for attending. Our next meeting is May 8th, 8 p.m. See you there.